Hello there, and welcome to the Sleepy Mystery Channel. Tonight, we'll be exploring some of the greatest mysteries of our universe and the strange questions that still sit beyond the edge of human understanding. This is a journey into the biggest unknowns we have ever faced. It reaches from the birth of time to the hidden forces that shape the space around us. The universe does not simply contain mysteries. In many ways, it seems built from them. Matter behaves in ways that challenge common sense. Space expands with a force we cannot fully explain, and distant signals arrive from places so far away that their sources remain unknown. Some ideas sound almost impossible at first. Hidden realities may exist beyond black holes, life may not be limited to Earth, and the rules behind everything may be stranger than they appear. If you enjoy these curious journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is get settled in. Let your shoulders soften. Let your breathing slow. And allow your mind to settle into stillness as we explore the deepest mysteries of the universe together. Let's begin. The universe may be far larger than we could ever possibly know. Every telescope shows us only the part of space whose light has had time to reach Earth. Beyond that visible boundary, there may be more galaxies, more clusters, and perhaps regions so distant that no signal from them will ever arrive. This does not mean they are imaginary. It means the universe may have places that are real, yet permanently hidden from observation. Some models suggest the unseen portion could be enormously bigger than the observable part. Others go further and imagine a cosmos that continues without end. That idea changes the feeling of everything. Our night sky becomes less like a complete map and more like a small window in a vast dark room. Some people even wonder whether what we call the universe is only one local region of a much larger structure. The mystery is simple, but almost impossible to absorb. We may never know the true size of existence. Dark matter holds galaxies together, yet nobody knows what it is. When astronomers measure how galaxies rotate, something does not add up. The outer stars move too quickly to be held in place by the visible matter alone. If only the stars, gas, and dust were present, many galaxies should tear themselves apart. Yet they do not. Something unseen appears to provide extra gravity, and it seems to outweigh ordinary matter by a huge margin. The name sounds confident, but it is really a placeholder for ignorance. It might be made of particles we have not detected. It might point toward a deeper problem with gravity itself. Some people even imagine hidden sectors of reality that interact with us only through their pore. Whatever the answer is, the mystery is not sitting at the edge of astronomy. It is built into almost every galaxy we can observe. The visible universe may be resting inside an invisible framework. Something is pushing space apart faster than anyone expected. For much of modern astronomy, many assume the expansion of space should slow down over time. Gravity pulls matter together, so the great outward motion from the early universe should gradually lose strength. Then, distant supernova revealed a shocking possibility. The expansion was not slowing as expected. It appeared to be speeding up. The unknown cause was given the name dark energy, but that label does not solve the problem. It only points to a force or property of space that remains deeply mysterious. It may be the energy of empty space itself. It may be a sign that our equations are missing something profound. It may even change over time in ways we cannot yet measure. The scale of this mystery is enormous because it affects the fate of everything. Galaxies, stars, and future observers may all be carried apart by something we still cannot properly describe. Black holes may contain entire hidden realities at their core. At the boundary of a black hole, known physics becomes strange, but still partly describable. Farther inward, the mystery becomes much deeper. Classical theory points toward a place where density becomes infinite and ordinary understanding breaks apart. Many physicists suspect that this cannot be the final answer. Something else may happen where the equations fail. Some proposals suggest a transition into a new region of space. Others imagine a bounce, a hidden interior, or a connection to another cosmic domain. These ideas are speculative, yet they come from a real problem. The heart of the black hole is not just difficult to see. It may be a place where space, time, gravity, and information stop behaving in familiar ways. Some people have wondered whether each black hole could contain the seed of a separate universe. That idea sounds wild, but the unanswered question underneath it is very serious. The universe seems tuned for existence with unsettling precision. Tiny changes in the basic properties of nature could have made a lifeless cosmos. If gravity had been much stronger, stars might have burned too fast. If it had been much weaker, matter might never have gathered into galaxies. The strengths of forces, the behavior of particles, and the balance of cosmic expansion all seem to allow long-lived stars and stable chemistry. This does not prove design, and scientists debate how to interpret it. Some say we notice these conditions only because we exist in a universe where noticing is possible. Others suggest there may be many universes with different settings, and we happen to live in one that permits observers. Some people take a stranger view and wonder whether mind, matter, and the laws of physics are connected more deeply than expected. The puzzle remains powerful because existence feels balanced on numbers that could have been otherwise. Signals from deep space keep arriving without clear origins. Astronomers sometimes detect brief bursts, repeating pulses, or unusual emissions from places that are hard to identify. Most are eventually linked to natural sources, but some arrive before the explanation is secure. That gap between detection and understanding is where the imagination wakes up. A signal may come from a collapsed star, a magnetic eruption, a distant galaxy, or an event we have not yet named. The hard part is that space is filled with extreme objects capable of producing energies far beyond anything on Earth. Even so, a few patterns feel especially puzzling when they repeat, vanish, or appear from surprising directions. Some people wonder whether an advanced civilization might leave traces in the radio sky. That idea is not the default answer, but it remains part of the larger question. In a universe this vast, every unexplained signal feels like a knock from somewhere beyond the familiar. Ancient Starlight shows a cosmos already full of surprises. Looking far into space also means looking far back in time. The most distant light began its journey when the universe was young, and it carries evidence from eras no human could ever visit. Each new generation of telescopes has pushed that view deeper, and the results have not always matched expectations. Some early galaxies appear brighter, heavier, or more organized than simple timelines once suggested. This does not mean the whole model is wrong, but it does show that the early universe may have been more active than expected. Stars could have formed quickly. Black holes could have grown rapidly. Gas may have collapsed into structure with surprising efficiency. For people who love the unknown, that is the exciting part. The past is not a settled chapter. It is still arriving in faint light, and each discovery can change the story of how the first cosmic structures came alive. Some scientists quietly wonder whether reality behaves like information. At the deepest levels of physics, information does not seem like a side detail. It may be central. Black holes raise the problem sharply because anything falling into them appears hidden, yet quantum theory says information should not simply vanish. This has led to ideas where the contents of a region may be encoded on a boundary, almost like a cosmic record written in a different form. That does not mean the universe is literally a computer, but it opens the door to startling comparisons. Particles, fields, and space itself may be linked through patterns of information more fundamental than ordinary matter. Some people take the thought further and imagine a simulated reality. Others stay closer to physics and ask whether space emerges from entanglement or hidden code-like structure. The fascination comes from a strange possibility. What seems solid around us may be the readable surface of something deeper. The Big Bang may not have been the beginning. The usual story says the universe expanded from an extremely hot and dense early state. Yet that does not automatically tell us what came before, or whether the word before even applies. The earliest moment we can describe is hidden behind conditions where our theories stop working together. Some models propose a cosmic bounce, where a previous universe contracted and then expanded again. Others imagine a larger inflating background where many cosmic regions form. There are also ideas in which time itself emerged from a deeper state, making the usual question impossible to frame. This mystery matters because beginnings shape meaning. If there was no first moment, the universe may be part of an endless cycle. If there was one, it may have arisen from laws we do not yet understand. Either way, the familiar origin story is not a closed door. It is a threshold, with darkness behind it. Space could be infinite in ways the human mind cannot picture. Infinity is easy to say and almost impossible to imagine. If space goes on forever, then every direction leads into endless distance, with no final wall and no outer edge. Under some interpretations, an infinite universe could contain endless variations of galaxies, stars, and planets. It could even contain regions where familiar patterns repeat by chance, though such ideas remain highly speculative. Other models suggest space might be finite but unbounded, meaning a traveler moving far enough in one direction could, in theory, return without ever finding an edge. The problem is that human intuition was built for rooms, roads, and horizons. The universe does not have to obey that scale of thinking. Measurements of cosmic geometry suggest space is very close to flat, but flatness does not prove infinity. The mystery remains open because the true shape of existence may extend beyond any test we can perform. Life appeared on Earth with a speed that still feels impossible. Earth formed from violent beginnings, yet signs of early life appear surprisingly close to the time when the planet became stable enough to support it. That raises a thrilling question. Was life almost inevitable once conditions were right, or did something extraordinarily rare happen here? The first living systems had to cross a strange boundary. Chemistry somehow became biology. Molecules began copying information, using energy, and building structures that could evolve. No one has fully recreated that transition from simple beginnings. Some researchers look to deep-sea vents. Others explore warm ponds, mineral surfaces, or impacts from space. Some people prefer the idea that life arrived from elsewhere, carried by comets or ancient debris. The wonder is not just that life exists now. It is that it may have taken hold so early, as if the planet was waiting for a spark that came almost as soon as it could. Dark energy may decide the final fate of everything. The future of the cosmos depends on a mysterious influence we do not understand. If dark energy remains steady, distant galaxies will keep slipping beyond reach, and the universe may become colder, darker, and increasingly isolated. If it grows stronger, it could one day overcome the bonds that hold cosmic structures together. If it weakens or changes character, the ending could be very different. This makes the problem more than a technical question. It is the hidden driver of the universe's long-term destiny. We can measure its effects through cosmic expansion, but its nature remains elusive. It might be a constant property of empty space. It might be a field that evolves. It might be a clue that gravity behaves differently across immense distances. Some people see it as the largest unknown force in existence. Whatever it is, the story of everything may be moving under its command. Galaxies spin as if invisible matter is guiding them. A spiral galaxy looks graceful, but its motion reveals a strange secret. Stars near the outer edge orbit faster than expected, almost as though they are held by a hidden mass spread through a vast halo. This pattern appears in galaxy after galaxy, making it one of the strongest clues that something unseen is present. Without that extra pull, the visible parts would not behave as they do. The mystery becomes even richer because this hidden component does not shine, absorb light, or reveal itself through ordinary signals. It acts through gravity and stays otherwise silent. Some researchers search for unknown particles. Others ask whether our understanding of motion changes at extremely low accelerations. Some people imagine invisible cosmic architecture surrounding the bright structures we admire. The rotation of galaxies turns a beautiful image into a puzzle. Every spinning disk seems to whisper that the visible matter is not in charge. The cosmic web looks strangely like a living network. On the largest scales, galaxies are not scattered randomly. They gather into vast filaments, clusters, and walls with immense empty regions between them. When mapped across deep space, the pattern resembles a network stretching through the observable universe. This structure grew from tiny early differences in density, amplified by gravity over cosmic time. Yet the result feels almost too organized for something born from slight variations. It has led some people to compare the large-scale cosmos with branching systems found in nature, although the physics behind each case is different. The fascination is not that the universe is alive in any ordinary sense. The fascination is that matter arranged itself into a connected form so vast that entire galaxies become like points along hidden threads. When we look at this web, we are not seeing objects in isolation. We are seeing the skeleton of cosmic history. Empty space may be filled with hidden activity. What looks like nothing may be one of the strangest parts of reality. In modern physics, a vacuum is not simply blank. Fields still exist there, and quantum effects suggest that empty regions can carry subtle energy and activity. Particles may briefly appear in mathematical descriptions before disappearing again, and forces can be affected by the structure of the vacuum itself. This changes the old idea of space as a silent stage where things happen. Space may be part of the performance. Some explanations for dark energy even point toward the energy of the vacuum, although the calculations produce deep puzzles. The mystery becomes more unsettling because nothingness turns out to be difficult to define. Remove matter, remove light, remove dust, and something still remains. Some people wonder whether hidden layers of reality are concealed inside what we casually call emptiness. The blank spaces of the cosmos may not be blank at all. Black holes might preserve information in ways we barely understand. For decades, black holes created a serious conflict between gravity and quantum theory. Anything crossing the boundary seems lost from the outside universe, yet quantum rules suggest that information cannot be destroyed. This tension became known as the information paradox. It sounds abstract, but it cuts to the heart of reality. If information can vanish, then the deep laws of physics may be incomplete. If it survives, then black holes must store or release it through a mechanism far stranger than ordinary intuition allows. Some ideas propose that information is encoded on the surface. Others suggest it escapes through subtle correlations in radiation. A few more speculative thoughts imagine that it passes into another region altogether. The important point is that black holes are not only cosmic drains. They may be testing grounds for the deepest rules of existence. Their darkness may be hiding a form of memory. Neutron stars may create matter stranger than anything on Earth. When a massive star collapses but does not become a black hole, it can leave behind an object of staggering density. A tiny amount of its material would outweigh mountains. Inside, atoms are crushed beyond normal form, and matter enters states that laboratories cannot fully reproduce. The outer layers may contain exotic crystals. Deeper down, particles could merge, transform, or arrange themselves in ways still debated. Some models describe superfluid interiors, where matter flows with almost no resistance. Others suggest forms involving strange quarks, creating material unlike anything in daily experience. These objects are not just heavy stars. They are natural experiments built by gravity itself. When two collide, they can shake space and forge heavy elements. Some people see them as cosmic alchemy chambers. Others see them as clues to hidden phases of matter. Their surfaces may look small in the sky, but their interiors are among the universe's deepest riddles. The first stars vanished before anyone could see them directly. The earliest stars were born from nearly pure hydrogen and helium before later generations filled space with heavier elements. They may have been enormous, brilliant, and short-lived. Because they formed so long ago, their direct light is extremely difficult to isolate, and none has been clearly observed as an individual object. Yet their influence should be everywhere. They helped transform the young universe, produced the first heavy elements, and prepared the raw material for later galaxies. Some may have collapsed into early black holes. Others may have exploded with energies unlike those of familiar stars. The mystery is powerful because these lost objects shaped the universe before the universe became recognizable. We study them through traces, models, and the effects they left behind. Some people imagine them as the first fires of creation. In practical terms, they were the ancestors of almost everything solid, including the matter that eventually became us. Some galaxies appear too mature for the early universe. When astronomers look at very distant galaxies, they are seeing them as they were billions of years ago. Some of these ancient systems seem unexpectedly bright, massive, or structured for their young age. That does not automatically overturn cosmology, because measurements can change and early data often improves. Still, the surprise is real enough to make researchers rethink how quickly galaxies can form. Maybe stars were born more efficiently in the early universe. Maybe dust, black holes, or gravitational lensing make some objects appear different than they are. Maybe the first cosmic neighborhoods grew faster than our simplest stories allowed. For anyone drawn to mysteries, this is a wonderful kind of problem. It does not close the book. It adds pages. The young universe was once imagined as a slower build toward complexity, but the evidence now suggests that some structures may have rushed into being with unexpected speed. Fast radio bursts arrive with power that seems almost impossible. A fast radio burst can release a huge amount of energy in a fraction of a second, then vanish before astronomers can easily study it. Some come once and are never heard again. Others repeat, which makes the puzzle even more interesting. The leading explanations involve extreme objects such as magnetars, but the full story is not settled for every case. Their signals can travel across enormous distances, carrying information about the space they passed through. That makes them useful tools as well as mysteries. Still, their suddenness gives them a dramatic quality. A distant galaxy flashes in radio light, Earth receives the pulse, and then the source may go silent. Some people naturally wonder whether artificial signals could hide among such bursts, although natural causes remain the serious starting point. The fascination lies in their power and brevity. They are cosmic messages that arrive almost too quickly to catch. The wow signal still has no agreed explanation. In the late 1970s, a radio telescope picked up a narrow signal from the direction of Sagittarius. It lasted long enough to be recorded, strong enough to stand out, and strange enough to earn its famous handwritten reaction in the margin. The signal was never confirmed again, which is part of why it remains so compelling. A one-time event is difficult to prove, yet also difficult to dismiss when it looks unusually clean. Many explanations have been suggested, including human interference, natural radio sources, or reflections from objects in our own solar system. None has settled the matter for everyone. For listeners who wonder whether another intelligence might briefly cross our instruments, this case has become almost legendary. It is not proof of contact. It is a doorway left half open. Something passed through our equipment that night, and the universe has not repeated the message clearly enough to end the argument. Time may have begun with an event we still cannot explain. We experience time as something obvious, because every thought seems to move through it. Yet when physics reaches back toward the earliest possible moment, time becomes one of the hardest ideas to hold. The hot beginning of the universe can be modeled to a point, but the very first instant remains hidden behind conditions where gravity and quantum theory both matter intensely. Some approaches suggest time began there, which would make the idea of an earlier moment meaningless. Others suggest time existed in a different form before our universe expanded. There are also proposals where time emerges from deeper relationships rather than sitting underneath everything as a permanent stage. This is why the mystery feels so enormous. The question is not only what happened at the origin, it is whether happening itself had to be born. The first tick of the cosmic clock may be beyond every ordinary way of thinking. Oumuamua behaved unlike any ordinary visitor from deep space. The first known interstellar object to pass through our solar system was already strange before the debate began. It came from outside the Sun's family, moved quickly, and followed a path that proved it was not a local asteroid. Then came the surprises. Its shape seemed unusual from the way its brightness changed. Its motion showed a slight push that was not easily matched to ordinary comet behavior. It did not display the obvious tail many expected. Natural explanations remain the main scientific focus, including icy material, unusual composition, or a thin fragment shaped by violent processes elsewhere. Still, the object was gone before we could study it closely. That left room for speculation. Some people famously wondered whether it might be artificial, or at least unlike anything our system normally produces. Whatever it was, it reminded humanity that deep space can send visitors with no warning and no return appointment. Rogue planets may drift between stars in unimaginable numbers. Not every world belongs to a solar system. Some planets may have been thrown away by gravitational chaos during their youth, while others may have formed alone in cold clouds of gas. These wandering objects travel through interstellar space without a parent star. At first, that sounds like a frozen fate, but the idea becomes more intriguing when you look closer. A thick atmosphere could trap internal heat. A buried ocean could survive under ice. A large moon might hold energy through tidal stress. Some people even wonder whether life could exist in places that never see a sunrise. Detecting these planets is difficult because they do not shine like stars, yet gravitational lensing has offered clues that they may be widespread. If their numbers are truly enormous, then the galaxy is not just filled with stars and orderly systems. It may also be filled with hidden worlds moving silently between them. Planet 9 may be hiding in the darkness beyond Neptune. Far beyond the known planets, some small icy bodies follow orbits that seem oddly grouped. One possible explanation is the gravitational influence of a large, unseen planet moving through the distant outer solar system. The idea is controversial, and not every researcher agrees that the evidence requires such a world. Observational bias may be shaping the pattern. The objects found so far might not represent the full picture. Yet the possibility is thrilling because it suggests our own solar system may still contain a major undiscovered planet. This would not be a bright world waiting in plain sight. It would be faint, cold, and slow, moving through a region where sunlight is barely useful. Some people connect the idea to older legends of hidden planets, although the modern search is based on orbital mathematics. The mystery feels personal because it is not in another galaxy. It may be on our own doorstep. The moon still raises questions about its violent birth. The leading explanation says, a Mars-sized body struck the young Earth and threw material into orbit, where it gathered into the moon. It is a powerful idea, but it still carries puzzles. Lunar rocks are surprisingly similar to Earth's mantle in some ways, which raises questions about how thoroughly the impact mixed the material. The moon is also unusually large compared with its planet, giving Earth a companion that shapes tides, stabilizes its tilt, and marks time across human history. Some refinements suggest a more extreme impact, a rapidly spinning early Earth, or a hot, vaporized structure that later cooled into two worlds. Some people go beyond science and wonder whether the moon's importance feels too perfect to be accidental. The sober truth is already dramatic enough. Our nearest celestial neighbor may be the frozen result of a collision so immense that it reshaped Earth and created the night sky we know. Mars may have lost a living world beneath its dust. Today, Mars looks dry, cold, and thin-aired, but the evidence of an earlier planet is everywhere. Ancient river channels, lake beds, minerals formed with water, and possible shorelines all point toward a past that was far more active. The greatest question is what that lost environment may have allowed. If Mars once had liquid water on the surface, a thicker atmosphere, and chemical energy, then simple life may have had a chance. The planet later changed, perhaps as its magnetic field faded and its atmosphere was stripped by the solar wind. That leaves open a haunting possibility. If life began there, it may have retreated underground as conditions worsened. Some missions have searched for chemical traces, while future samples may reveal more. Some people even wonder whether Mars and Earth exchanged early life through impact debris. The red world may not be dead in the simple way it appears. Europa may hide an ocean, while life could still wait. Jupiter's icy moon has one of the most exciting hidden environments in the solar system. Its surface is cracked, bright, and young, suggesting movement from below. Beneath the ice, a global ocean may surround the entire moon. The source of warmth is not sunlight, because Europa is too far from the sun for that. Instead, Jupiter's gravity pulls and flexes the moon, creating internal heat through tidal forces. That means water, energy, and chemistry may exist together in a buried sea. On Earth, life can survive near deep ocean vents without sunlight, which makes Europa especially tempting. No one is saying there are creatures swimming there with certainty. The mystery is more careful and more exciting. A world that looks frozen from the outside may contain one of the best places to search for alien biology. The answer could be sealed under ice that has been hiding it for ages. Enceladus sends watery plumes into space, like quiet invitations. Saturn's small moon surprised scientists by spraying material from cracks near its south pole. Those plumes contain water vapor, ice grains, salts, and organic molecules, which strongly suggest a subsurface ocean beneath the frozen crust. This is extraordinary, because Enceladus offers access to its hidden sea without drilling through miles of ice. A spacecraft can fly through the spray and sample clues carried up from below. The moon is tiny compared with major planets, yet it may have internal heat, liquid water, and chemistry that invites serious astrobiology. Some interpretations even point toward hydrothermal activity on the ocean floor, which would make it resemble places on Earth where life thrives in darkness. The mystery is no longer whether this world is interesting. It is whether its hidden ocean is merely chemical, or something more. Enceladus has become one of the rare places where a buried environment reaches outward into space. Titan has lakes and weather made from alien chemistry. Saturn's largest moon is familiar and deeply strange at the same time. It has a thick atmosphere, clouds, rain, rivers, and lakes, but the liquid on its surface is not water. It is mostly methane and ethane, behaving in a cold cycle that faintly echoes Earth's water cycle. Beneath the icy crust, Titan may also hide a water-rich ocean, giving it two very different chemical worlds in one place. The surface is shaped by dunes, shorelines, and changing weather, yet the temperatures are far too low for ordinary biology as we know it. That has not stopped speculation. Some people wonder whether exotic life could use methane in ways Earth life uses water, although that remains uncertain. Titan matters because it expands the imagination of habitability. It shows that a world can be active, complex, and planet-like, even when its chemistry feels completely foreign to us. Venus may once have been a far gentler world. Venus is now a furnace beneath crushing clouds, but some models suggest it may not always have been that way. Long ago, it could have had milder conditions and perhaps even surface water. If that is true, then Venus may represent one of the great planetary tragedies. A world close in size to Earth may have crossed a climatic threshold and never recovered. The mystery is difficult because Venus destroys many spacecraft quickly, and its surface is hidden beneath a thick atmosphere. Researchers study its chemistry, volcanic plains, and possible past rotation to understand how it changed. Some debate whether clouds today could contain unusual chemical signatures, though the interpretation remains contested. For people drawn to cosmic what-ifs, Venus is irresistible. It asks whether Earth's twin once had a calmer chapter, and whether a habitable world can become unrecognizable when its atmosphere turns against it. Mercury has ice hiding in places sunlight never reaches. The closest planet to the Sun seems like the last place to find frozen water. Its daytime surface can become intensely hot, yet radar observations and spacecraft data show ice in permanently shadowed craters near the poles. Because Mercury has almost no atmosphere and very little axial tilt, some crater floors never receive direct sunlight. They remain cold enough to preserve volatile material for immense lengths of time. The ice may have arrived through comet impacts, asteroid delivery, or chemical processes involving the solar wind. This creates a beautifully odd contrast. On one part of Mercury, rocks bake under fierce sunlight. In another, ancient ice survives in darkness. The discovery changed how scientists think about small, airless worlds. It also hints that the solar system stores memory in unexpected places. Even the planet nearest the Sun keeps secrets locked away where the light cannot reach. Jupiter shields Earth, but it may also send danger inward. Jupiter is often imagined as Earth's guardian because its powerful gravity can redirect comets and asteroids. In some cases, it may capture or fling away objects that might otherwise wander closer to the inner solar system. Yet the story is not that simple. The same giant planet can also disturb small bodies and send them into new paths. Its gravity shapes asteroid families, affects comet orbits, and has influenced the architecture of the solar system from the beginning. This makes Jupiter both protector and troublemaker. Without it, Earth's history might have been calmer in some ways and more dangerous in others. The mystery is not whether Jupiter matters. It is how its long gravitational influence changed the chances for life here. Some people even wonder whether a massive outer planet is necessary for worlds like Earth. The answer may decide how we judge distant solar systems that look nothing like ours. Saturn's rings are younger than many scientists expected. Saturn feels timeless because its rings look so grand and permanent, but they may be a recent feature in cosmic terms. Measurements of their mass, brightness, and contamination by dark dust suggest they could be much younger than the planet itself. Some estimates place their origin within the age of the dinosaurs, although the debate is still active. This is startling because it means Saturn may once have looked very different. The rings could have formed from a shattered moon, a disrupted icy body, or a collision that spread debris into orbit. They are also slowly changing as material falls into Saturn or spreads outward. The most famous site in the solar system may be temporary. That makes it feel almost lucky that humans evolved during the era when telescopes could see it. Some people find a strange meaning in that timing. The universe may show its wonders only for a season. Uranus spins sideways after a collision nobody witnessed. Most planets rotate with their poles roughly upright, compared with their path around the Sun. Uranus does something far stranger. It rolls on its side, with an extreme axial tilt that gives it seasons unlike those of any other major planet. The usual explanation is a massive ancient impact, possibly with an Earth-sized body, during the early chaos of solar system formation. Yet details remain uncertain. A single impact may explain some features but not others. Multiple collisions, gravitational effects, or changes involving a former moon have also been discussed. Uranus is difficult to study because it is distant and has only been visited once by spacecraft. Its tilted magnetic field adds another layer of strangeness. The result is a planet that looks calm through a telescope but carries the signature of a forgotten catastrophe. Somewhere in its deep past, a violent event may have turned an entire world sideways. Neptune gives off more heat than it receives from the Sun. At the edge of the major planets, Neptune receives faint sunlight, yet it has powerful winds and emits more energy than it takes in. This internal heat helps drive one of the most dynamic atmospheres in the solar system. The exact source and behavior of that heat remain active questions. It may be leftover warmth from formation, slow contraction, or processes deep inside the planet. Neptune also has storms that appear and fade, including dark spots that behave differently from Jupiter's long-lived features. Its moon, Triton, adds further intrigue because it may have been captured from the outer solar system and could possess internal activity of its own. Neptune feels remote, but it is not dormant. It is a blue world with a hidden engine. Some people see it as proof that distance from the Sun does not define a planet's energy. The outer darkness still has weather, motion, and unanswered force. Pluto may still have a hidden ocean beneath its heart. When the first close images of Pluto arrived, they transformed a distant dot into a complex world. Its bright heart-shaped region, icy plains, mountains of water ice, and varied terrain showed that Pluto was not simply a frozen relic. One of the most surprising possibilities is that it may still contain a subsurface ocean. For a body so small and far from the Sun, that idea once sounded unlikely. Yet signs of geological youth, possible cryovolcanic features, and the behavior of its icy shell have kept the theory alive. A hidden ocean would mean that internal heat survived in ways not fully expected. It would also blur the line between planets, dwarf planets, and potentially habitable environments. Some people love Pluto because it resists being reduced. It lost its old planetary status, then gained a deeper mystery. Beneath its frozen face, there may be liquid water held in the dark. Comets may have delivered key ingredients for life on Earth. Comets are often described as icy leftovers from the solar system's formation, but they may have played a more active role in Earth's story. Early in our planet's history, impacts from comets and asteroids could have brought water, carbon-rich molecules, and other ingredients that later became important for biology. The exact contribution is debated because Earth also had internal sources, and not all comet chemistry matches our oceans perfectly. Still, the idea is powerful. Instead of life's ingredients being purely local, some may have arrived from distant frozen bodies that formed far from the young sun. Laboratory studies and space missions have found organic compounds in comet material, strengthening the sense that these objects are chemical messengers. Some people take the thought further and wonder whether primitive life itself could travel between worlds. The careful version is already amazing. Our living planet may have been seasoned by ancient visitors from the outer cold. Asteroids could be ancient records from before planets formed. Unlike planets, many asteroids never melted fully or changed beyond recognition. That makes them valuable fragments of the early solar system. Some preserve minerals, metals, and chemical patterns that date back to the time before Earth took its final form. When missions return samples from asteroids, they are not merely collecting rocks. They are bringing home evidence from the construction era of the Sun's family. These bodies can reveal how dust became pebbles, how pebbles became larger objects, and how planets assembled through collisions. Some contain water-bearing minerals or organic material. Others are metallic remnants of worlds that may have been shattered. For people drawn to hidden histories, asteroids are like scattered pages from a destroyed archive. They circle the sun quietly, but they remember conditions that no longer exist. Each one may carry a different clue about how ordinary matter became worlds, moons, oceans, and eventually observers. Meteorites sometimes carry organic clues from deep cosmic history. When a meteorite lands on Earth, it can bring material older than our planet. Some meteorites contain amino acids, carbon compounds, and tiny grains that formed around ancient stars before the solar system existed. These discoveries do not prove that life came from space, but they show that important chemistry is not confined to Earth. The ingredients for biology can form in cold clouds, in asteroid parent bodies, and in environments far removed from living worlds. That widens the mystery of life's origin. Perhaps Earth was not a special chemical exception. Perhaps the galaxy is scattered with pieces of prebiotic possibility. Care is needed because contamination can complicate the study of fallen rocks, so scientists examine fresh samples with strict methods. Still, the idea is thrilling. A stone crossing the sky may not be just a dramatic visitor. It may be carrying molecular memories from eras before the sun was born. The sun's long cycles may affect Earth in hidden ways. The sun is not a steady lamp. It changes through cycles of magnetic activity that influence sunspots, radiation, solar wind, and eruptions. The most familiar cycle lasts about 11 years, but longer patterns may also exist. These variations can affect satellites, radio communication, auroras, and the upper atmosphere. The more difficult question is how strongly solar behavior influences Earth's climate and biological history over long periods. Mainstream science separates solar effects from other drivers carefully, but the discussion remains complex. Some people suspect the sun's deeper rhythms are underappreciated, perhaps linking magnetic shifts with patterns in weather, earthquakes, or human history. Those claims often go beyond what evidence can firmly support, yet the fascination is understandable. Our star is the main energy source for the planet, and it is magnetically alive. Earth may be more tightly connected to solar moods than everyday life allows us to notice. solar storms could change modern life in a single day. A powerful eruption from the Sun can send charged particles and magnetic disturbance toward Earth. If the event is strong enough, it can disrupt power grids, satellites, navigation systems, radio signals, and communications. History gives a famous warning through the Carrington event of the 19th century, when telegraph systems were affected by a geomagnetic storm. Today, the same kind of event could strike a world filled with electrical infrastructure. The danger is not dramatic in the way a movie imagines it. It is more unsettling because it involves invisible forces arriving from a star we depend on. A beautiful aurora could appear far from the poles, while engineers struggle to protect systems that keep modern society connected. Space weather forecasting has improved, but uncertainty remains. Some people see this as a reminder that civilization is younger and more fragile than it feels. One solar outburst could reveal our hidden dependence on the sky. The heliosphere may be protecting us from mysterious cosmic rays. The Sun surrounds the solar system with a vast bubble created by the solar wind. This region helps shape how charged particles from interstellar space reach the planets. Beyond it, cosmic rays travel through the galaxy with high energies and uncertain origins. Some come from supernova remnants or other violent sources, but not every detail is settled. The heliosphere acts like a shifting shield, influenced by the Sun's activity and the conditions of nearby interstellar space. This means Earth is not simply orbiting inside empty darkness. It is living inside a magnetic environment that changes over time. When the Sun's activity rises or falls, the amount of cosmic radiation entering the inner solar system can change as well. Some people wonder whether these changes could affect clouds, climate, or even evolution over long spans. The evidence is debated, but the larger idea is fascinating. Our solar system may be wrapped in an invisible protective boundary. Voyager found strange surprises near the edge of the solar system. The Voyager spacecraft were launched to visit the outer planets, but their journey did not end there. They continued outward until they reached the boundary region where the Sun's influence gives way to interstellar space. Scientists expected important discoveries, yet the details were more complicated than simple diagrams suggested. The magnetic field did not behave exactly as predicted. Particle levels changed in surprising ways. The transition from solar territory to the wider galaxy turned out to be layered and dynamic. These old spacecraft are now among humanity's most distant messengers, carrying instruments, records, and a symbolic greeting into the unknown. Their data is precious because no other machines have directly explored that region in the same way. Some people see Voyager as more than engineering. It is a test of whether a young species can send a whisper beyond its cradle. At the edge of the solar system, the familiar became strange again. Interstellar space is not as empty as it sounds. Between the stars, there is no air to breathe and no world to stand on, yet the region is not a perfect void. It contains thin gas, dust grains, magnetic fields, cosmic rays, and vast clouds where future stars may form. The density is incredibly low by Earth standards, but across immense distances even faint material can matter. Starlight passes through it and carries marks of what it encountered. Shock waves move through it after stellar explosions. Molecules form in cold, shadowed clouds, including some that connect to the chemistry of life. This means the spaces between stars are part of the cosmic story, not empty gaps between important places. Some people imagine interstellar space as a hidden ocean with currents too subtle for human senses. It may shape where stars are born, how radiation travels, and how galaxies evolve. The darkness between suns is not nothing. It is a thin, active medium. Cosmic rays arrive with energies that challenge known sources. High-energy particles constantly strike Earth from space, but the most extreme ones are difficult to explain. Some carry energies far beyond what human machines can produce, and they arrive after traveling through magnetic fields that bend their paths. That makes their sources hard to trace. Violent objects such as supernova remnants, active galaxies, and powerful jets are likely suspects, but the exact origin of the highest energy events remains uncertain. When one of these particles enters Earth's atmosphere, it creates a shower of secondary particles that can spread across wide areas. Detectors capture the aftermath, like hearing an echo instead of seeing the original cause. Some people wonder whether unknown physics or exotic cosmic engines are involved. Even the cautious explanations are astonishing. Somewhere in the universe, nature is accelerating tiny particles with a force that makes our greatest laboratories look small. Every impact is a clue from an unseen accelerator. Antimatter exists, but the universe seems strangely short of it. For every familiar particle, physics allows a counterpart with opposite charge. When matter and antimatter meet, they can annihilate into energy. The strange part is that the early universe should have produced both in enormous amounts. If they were created equally, almost everything might have vanished in mutual destruction, leaving little more than radiation behind. Instead, ordinary matter survived and built stars, planets, and people. This means there must have been a slight imbalance, or some process that favored matter over antimatter. Experiments have found differences in particle behavior, but not enough to fully explain the cosmic result. The missing antimatter problem raises a deep question about why anything material exists at all. Some people imagine distant regions made of antimatter, although observations make large nearby domains unlikely. Still, the mystery remains gripping. The universe may be here because reality leaned by a tiny amount in one direction. The missing antimatter problem points toward a deeper imbalance. The survival of matter may depend on a subtle asymmetry built into the laws of nature. In the early cosmos, particle reactions had to create a tiny excess of matter over antimatter. The difference may have been incredibly small, yet after annihilation it would have become everything we now see. Galaxies, oceans, bodies, and instruments all trace back to that slight preference. The challenge is explaining where it came from. Some theories involve rare particle decays. Others require conditions that existed only at extreme temperatures near the beginning of cosmic history. There are also ideas involving neutrinos, which may behave in ways that help solve the puzzle. The mystery is not only mathematical, it feels almost personal. Existence itself may be the leftover from an ancient imbalance. Some people see in that imbalance a clue that the universe is not perfectly neutral at its core. Something chose a side, even if only through physics. Gravity remains the force that refuses to fit neatly. Gravity is the force we feel most directly, yet it is also the one that resists full unification with the quantum world. Einstein described it as the curvature of space-time, and that explanation works beautifully for planets, stars, and galaxies. Quantum theory works beautifully for particles and fields. The problem is that both are needed in extreme places, such as the earliest universe and the centers of black holes. There, our best descriptions no longer fit together cleanly. Many approaches try to solve this, including strings, loops, emergent gravity, and other ideas that stretch ordinary imagination. None has become the final answer. This makes gravity feel almost deceptively familiar. It holds your feet to the floor, guides the moon, and bends light from distant galaxies. Yet underneath that everyday pull may be the missing key to reality. The most common force in our lives may still be hiding its deepest nature. Quantum particles seem connected across distances that defy intuition. In the quantum world, two particles can share a linked state even after they separate. When one is measured, the other shows a related result in a way that cannot be explained by ordinary local hidden instructions. This does not allow simple faster-than-light messaging, but it does challenge the old picture of objects carrying fully independent properties through space. Experiments have tested this connection again and again, closing loopholes and strengthening the conclusion. The universe appears to permit relationships that are not limited by everyday distance in the way common sense expects. Some people see this as a hint that space is not the deepest layer of reality. Maybe separation is partly emergent. Maybe the world is woven through relationships before it appears as location. The mystery is powerful because it has been tested, not merely imagined. Tiny particles seem to know something about togetherness that the larger world teaches us to forget. Entanglement makes the universe feel less separate than it appears. The deeper scientists look into quantum behavior, the less the universe resembles a collection of isolated objects. Two particles can share one linked description, even when they are moved far apart. The strange part is not that they communicate like radios. That would be easier to understand. The strange part is that the connection seems to exist before ordinary distance has the final say. This has been tested with careful experiments, and the results keep pointing away from the simple idea that every object carries its own complete private reality. Some people hear this and wonder whether the universe is more like one system wearing many masks. Others stay closer to physics and describe it as a clue about how nature stores relationships. Either way, the feeling is profound. What looks separate may be joined at a level below sight, touch, and common sense. The double-slit experiment still unsettles common sense. A beam of tiny particles is aimed at two narrow openings, and the result should be simple. Each particle should pass through one slit or the other, like a grain of sand through a gap. Instead, when the path is not checked, the pattern on the screen looks like waves overlapping. When the path is measured, the pattern changes. This is not just a classroom trick. It is one of the most famous demonstrations that matter does not behave according to everyday expectations. Electrons, photons, and even larger particles can show this strange split between wave-like possibility and definite outcome. Some interpret it as a measurement problem. Others see it as a sign that reality only becomes fixed under certain conditions. Some people take a more radical view and wonder whether consciousness has a role. The experiment remains fascinating because it is simple to describe, yet almost impossible to truly explain. Observation may play a stranger role than anyone expected. In ordinary life, looking at something does not seem to change what it is. A chair is still a chair whether anyone notices it or not. At quantum scales, the act of measurement becomes harder to separate from the thing being measured. The problem is not only human eyesight. It can involve any interaction that forces a system to give a definite result. Before that point, quantum theory often describes a spread of possibilities rather than one clear state. This has led to many interpretations, each trying to explain what really happens when possibility becomes outcome. Some suggest that the world branches. Some propose hidden mechanisms. Others treat the question as a limit of what can be meaningfully said. For people who enjoy the edge of mystery, this is irresistible. Reality may not simply sit there waiting to be seen. It may participate in the moment it becomes known. Reality may not exist in one fixed state until measured. Quantum theory allows a system to be described as multiple possibilities at once until a measurement produces a definite result. This does not mean large objects casually flicker between forms in daily life. The familiar world is stabilized by constant interaction with its surroundings. Still, the underlying question remains unsettling. What is a physical state before it becomes an observed outcome? In the famous thought experiment involving a cat in a box, the point is not really the animal. The point is the absurdity of applying quantum uncertainty to ordinary reality. Different interpretations offer different answers. One says there are many branching outcomes. Another says the wave function collapses. Another says the problem reflects what observers can know. Some people hear these ideas and feel that matter itself is less solid than it appears. The mystery is not whether the equations work. They do. The mystery is what they are telling us about existence. The Planck scale may hide the smallest structure of existence. There is a distance so tiny that our usual ideas of space may stop making sense. It is called the Planck length, and it marks a boundary where gravity and quantum effects may become inseparable. No instrument can directly probe it in any ordinary way. It is far smaller than particles we can currently study. Yet many theories suggest that something important happens there. Space may not be smooth all the way down. It may have a hidden texture, a foam-like behavior, or a structure unlike anything our language can easily describe. This matters because every larger thing may depend on what happens at that smallest level. Mountains, stars, and galaxies would all be built upon rules operating beneath the reach of direct measurement. Some people imagine the Planck scale as the locked basement of reality. We know the door exists through mathematics, but we do not yet know what is inside. Space itself may come in tiny, indivisible units. We usually think of space as something that can be divided forever. Take a length, cut it in half, then repeat the process endlessly. Yet some approaches to quantum gravity suggest there may be a smallest meaningful unit of area or volume. If true, space would not be perfectly continuous. It would have a granular foundation, although not like grains of sand floating in emptiness. The idea is stranger than that. The stage on which everything happens might itself be built from discrete relationships. This could help explain what happens in extreme conditions where smooth space-time breaks down. It could also change how we understand the early universe and black hole interiors. Some people hear this and picture reality as a kind of cosmic mosaic. That picture is only a metaphor, but it points toward an astonishing thought. The open room around you may be made from something that cannot be cut smaller. Time could be an emergent effect rather than a foundation. Time feels basic because every experience depends on before and after. Yet some physicists suspect time may not be fundamental. It could arise from deeper relationships, much like temperature arises from the motion of many particles. One particle does not have a temperature in the everyday sense. A large collection does. In a similar way, time may appear when more basic ingredients are arranged in certain patterns. This possibility changes everything. Instead of asking what happened inside time, we may need to ask how time came to exist at all. The idea appears in several approaches to quantum gravity, where the equations sometimes seem timeless at the deepest level. Some people take this as a clue that past, present, and future may be less separate than they feel. Others see it as a mathematical warning. Either way, the mystery is enormous. The clock may not be the foundation of the universe. It may be a feature that emerged. The arrow of time still points in only one direction. The laws of physics often work almost the same whether time runs forward or backward. Yet daily experience does not. A broken cup does not reassemble itself. Smoke does not gather back into a flame. Memories point toward the past, never the future. This one-way flow is called the arrow of time, and it is closely tied to disorder increasing in closed systems. The puzzle is why the universe began in such an ordered condition that this arrow could exist at all. Without that special starting state, the direction of time might not feel so obvious. Some people wonder whether time's direction is only a local feature of our cosmic region. Others think it is bound to the deepest origin of the universe. The mystery touches everything because no one can step outside it. We do not merely observe the arrow of time. We are carried by it with every breath. Entropy may explain time, but not why time exists. Entropy gives us one of the best clues to why the future feels different from the past. As systems evolve, usable order tends to spread out. Ice melts in warm water. Heat disperses through a room. Stars burn their fuel and move toward exhaustion. This helps explain why events appear irreversible. Yet entropy does not answer the deeper question by itself. It tells us how time behaves inside the universe, but not why there is a temporal dimension in the first place. It also depends on the universe beginning in a very low entropy state, which remains one of the great cosmic puzzles. Some people see this as a hidden fingerprint of a special beginning. Others think a larger cosmic cycle may set the conditions. The fascination is that time may be both familiar and unexplained. We can measure it precisely, but its deepest source remains out of reach. Wormholes might connect distant places through hidden shortcuts. Einstein's equations allow strange possibilities, where space-time could bend into a tunnel between separate regions. A wormhole would not be a normal passage through space. It would be a shortcut made from the structure of space itself. In theory, such a bridge might link distant locations, or even different times, although keeping it open may require exotic conditions that may not exist naturally. No confirmed wormhole has ever been found. Still, the idea persists because it grows from serious mathematics, not only imagination. Black holes, quantum effects, and the shape of space-time all keep the conversation alive. Some people wonder whether advanced civilizations could use such passages. Others ask whether microscopic wormholes might appear briefly at the smallest scales. The mystery is thrilling because it suggests distance may not be absolute. The universe may have hidden routes that do not appear on any map made by light. White holes may be the opposite of black holes. A black hole lets things enter but not escape once they cross the boundary. A white hole would be the reverse. Nothing could enter it from outside, but matter and energy could emerge from it. This idea appears in certain solutions to the equations of relativity, although no one has observed such an object. Many physicists consider them unlikely as stable, real features of the cosmos. Yet they remain fascinating because they open strange doors in theory. Could the beginning of our universe resemble a white hole from another perspective? Could a collapsing black hole somehow transform into an explosive release far in the future? These ideas are speculative, but they reveal how flexible space-time can become at the edge of known physics. Some people imagine white holes as cosmic fountains. The safer statement is still remarkable. Nature's equations permit an object that runs against the behavior we associate with gravity's darkest places. Cosmic strings could be ancient scars from the young universe. In the first moments after the universe began expanding, reality may have gone through dramatic phase changes. If so, defects could have formed in the fabric of fields, somewhat like cracks that appear when water freezes. Cosmic strings would be incredibly thin, incredibly dense lines stretching across space. They have not been confirmed, but if they exist, they could leave subtle traces through gravitational effects, lensing patterns, or ripples in space-time. The idea is compelling because it turns the early universe into a place with leftover marks. Not everything from that era would have faded smoothly. Some structures might remain as relics from a time when the rules of nature were settling into their present form. Some people imagine them as seams in reality, although that is only a way to picture the concept. The real mystery is whether space still carries scars from its first transformations. Magnetic monopoles are predicted, but nobody has found one. Every magnet we know has a north pole and a south pole together. Cut a magnet in half, and each piece becomes a smaller magnet with both poles again. Yet some theories predict a particle that would carry only one magnetic pole by itself. Such a discovery would be revolutionary, because it would explain certain features of electric charge and support ideas about the early universe. Searches have been carried out in rocks, cosmic rays, particle detectors, and ancient materials. So far, no confirmed monopole has appeared. That absence is interesting in its own right. If they were created in the early universe, where did they go? Inflation may have diluted them until they became almost impossible to find. Or perhaps the theories predicting them are pointing in the wrong direction. Some people love this mystery because it is so clear. Physics has left a place for a missing object, and nature has not yet filled it. The universe may contain dimensions we cannot directly perceive. Human experience gives us 3 dimensions of space and 1 of time, but physics does not always stop there. Some theories allow extra-spatial dimensions that are curled up, hidden, or accessible only through gravity and high-energy processes. These dimensions would not be directions we can point to in daily life. They might be too small to notice, or arranged in ways that keep ordinary matter confined to the world we know. The idea can sound like fantasy, yet it appears in serious attempts to unify the forces of nature. It also gives speculative thinkers a vast playground. Hidden dimensions could change how we think about particles, black holes, and the origin of physical laws. Some people wonder whether unexplained phenomena might be glimpses of a larger structure. Evidence has not confirmed that view, but the possibility remains captivating. Reality may have more room than our senses can report. String theory suggests reality may vibrate beneath ordinary matter. In string theory, the smallest ingredients are not point-like particles. They are tiny vibrating strings with different patterns producing different particles. An electron, a quark, or another particle would be like a note played by the same underlying instrument. The idea is elegant because it can include gravity in a quantum framework, which is one of physics' hardest goals. Yet it also requires extra dimensions and operates at scales far beyond direct testing. This leaves it in a strange position. It is mathematically rich and deeply influential, but not confirmed by experiment. Some people see it as a glimpse of a hidden musical order behind matter. Others criticize it for being too flexible to prove. The mystery is not merely whether the theory is right. It is whether nature really has a single underlying language that turns vibration into substance, force, and the familiar world of experience. The multiverse could place our universe among countless others. The word universe once meant everything that exists. Modern theory has complicated that idea. Some models suggest our observable cosmos could be only one region within a larger reality containing many separate universes. They might have different physical constants, different particles, or completely different histories. We may never be able to visit them, and direct evidence is extremely difficult. Still, the concept has grown from attempts to explain inflation, quantum mechanics, and the strange fine-tuning of our own world. If many universes exist, then our cosmic conditions may be one outcome among a vast range of possibilities. Some people find that humbling. Others find it unsettling because it pushes explanation into places we cannot observe. The idea also appeals to anyone who suspects reality is bigger than the official map. The multiverse is not proven, but it has changed the question. Perhaps the cosmos we study is not the whole story. Parallel worlds may exist beyond the reach of every telescope. One interpretation of quantum mechanics suggests that every possible outcome occurs in a branching structure of reality. In that view, the universe does not choose one result while discarding the others. Instead, all outcomes continue in separate branches that no longer interact in ordinary ways. This is often called the many worlds interpretation. It does not require hidden planets or distant galaxies beyond our sight. The parallel worlds would be linked to quantum possibility itself. The idea is controversial, partly because testing it is extremely difficult. Yet it offers a clean way to avoid the mysterious collapse of the wave function. Some people hear it and immediately imagine other versions of their own lives. The serious theory is more subtle than that, but the emotional pull is obvious. If this interpretation is true, reality is not a single road. It is a branching structure beyond every telescope and every familiar sense. Inflation may have expanded space faster than light itself. Very early in cosmic history, space may have undergone a brief burst of extreme expansion. This idea helps explain why the universe looks so uniform across regions that should not have had time to communicate. It also helps explain why space appears so close to flat on large scales. Nothing is said to move through space faster than light during this process. Instead, space itself stretches, carrying regions apart at extraordinary speed. The theory has strong appeal, but the details remain debated. What field drove inflation? How did it start? How did it stop? Did it happen once, or does it continue elsewhere? These questions turn a successful idea into a doorway toward larger mysteries. Some people imagine inflation as the moment our cosmic region was blown open from a tiny seed. Whether or not that picture is exact, the concept suggests the universe may have grown from something unimaginably small with stunning speed. Eternal inflation could keep creating universes without end. Some versions of inflation do not stop everywhere at once. In this view, certain regions settle into universes like ours, while other regions continue inflating. That continuing process could produce bubble universes again and again, each separated from the others by expanding space. The result is a multiverse with no simple final boundary. Our universe would be one pocket where inflation ended locally, allowing particles, stars, and galaxies to form. Elsewhere, the process might still be happening. This idea is difficult to test, but it follows naturally from some inflationary models. It also gives cosmic origin a strange new feeling. The beginning of our universe may not have been the beginning of everything. It may have been one event in a larger generative process. Some people find this almost impossible to absorb. Creation would not be a single moment. It would be a continuing activity unfolding beyond every horizon we can reach. The cosmic microwave background contains patterns still being debated. After the early universe cooled enough for light to travel freely, that ancient radiation began crossing space. Today, we detect it as a faint microwave glow from every direction. It is one of the strongest pieces of evidence for the hot, early universe, but it is also full of subtle patterns. Tiny temperature variations reveal the seeds of later structure. They help measure the age, composition, and geometry of the cosmos. Yet some features have inspired debate because they appear unusual or unexpected. Researchers study whether these are meaningful signals, statistical flukes, measurement effects, or hints of deeper physics. For mystery lovers, this background radiation feels like a baby picture of everything. It is not a smooth, blank glow. It is a coded surface carrying ancient information. Some people search it for signs of cosmic collisions, hidden cycles, or fingerprints from beyond our universe. The oldest light still has secrets left inside it. The cold spot may be a bruise from another universe. One region of the cosmic microwave background appears cooler than expected across a surprisingly broad area. There are possible conventional explanations, including a large cosmic void between us and that patch of ancient radiation. Yet the feature has also inspired a more dramatic possibility. Some have suggested it could be evidence of a collision between our universe and another bubble universe in the distant past. That interpretation is speculative and far from settled, but it captures the imagination because the signal is not invented. The cold region is there. The debate is over what caused it. Perhaps it is a statistical oddity. Perhaps it reflects intervening cosmic structure. Or perhaps it is the faint mark of something beyond our cosmic boundary. The power of this mystery comes from that range of possibilities. A patch of colder, ancient light has become a screen onto which the biggest questions in cosmology are projected. The axis of evil seems to challenge cosmic randomness. The universe is expected to look broadly the same in every direction when viewed on the largest scales. Yet certain large-scale patterns in the cosmic microwave background appear oddly aligned. This controversial feature has been given the dramatic nickname, the axis of evil. The name sounds theatrical, but the issue is technical and serious. Are the patterns real cosmic clues, or are they artifacts from measurement, data processing, foreground contamination, or statistical chance? Different studies have debated the strength and meaning of the alignment. If it were truly fundamental, it might suggest that the universe has a preferred direction, which would challenge a major assumption in cosmology. Most scientists are cautious, but the mystery remains intriguing. Some people see it as a hint that the cosmos is less random than advertised. At minimum, it reminds us that even the best maps of ancient light can contain surprises that refuse quick dismissal. Some galaxy alignments appear too organized to ignore. Across huge distances, astronomers have found cases where galaxies, quasars, or their rotation axis seem aligned in unexpected ways. Not every claimed pattern survives closer study, but some have raised real questions about how structure forms on very large scales. A standard picture allows gravity to build filaments and clusters from early density variations. Still, certain alignments appear to stretch across distances that challenge simple expectations. They may result from cosmic web dynamics, selection effects, measurement bias, or unknown features of early conditions. The mystery is tempting because alignment feels meaningful to the human mind. When objects across space point or spin in related ways, it is hard not to wonder whether a deeper order is present. Some people imagine hidden fields guiding cosmic structure. More cautious voices ask whether our surveys are still incomplete. Either way, these patterns matter because they test the idea that the largest universe is directionless and random. The Great Attractor is pulling galaxies toward an unseen region. Our galaxy and many nearby galaxies are moving in a direction that points toward a massive concentration of matter. The region became known as the Great Attractor, although the name makes it sound more like a science fiction force than a gravitational landscape. Part of the challenge is that our view is blocked by the Milky Way's own dust and stars, which hide objects behind the galactic plane. Over time, astronomers have mapped more of the area and found clusters that help explain the motion. Still, the full flow of galaxies involves even larger structures beyond it. The mystery is compelling because Earth is not simply sitting still in space. We are riding inside a galaxy that is being drawn through the cosmos by masses we cannot easily see. Some people imagine hidden engines or unseen architecture. The grounded truth is already strange. Whole galaxies are streaming toward something partly concealed from view. The Shapley supercluster may be part of an even larger pool. Beyond the region first associated with the Great Attractor lies an enormous concentration of galaxies, known as the Shapley supercluster. It is one of the most massive structures in the nearby universe, and it appears to play an important role in the motion of our local cosmic neighborhood. The discovery shifted attention from a single attractor to a larger pattern of gravitational flow. Galaxies do not move only because of what is close. They respond to mass distributed across vast distances. This makes the universe feel less like scattered islands and more like a connected landscape with slopes we cannot see directly. Some people wonder whether even Shapley is only part of a grander movement towards still larger structures. The data suggests a complex cosmic current rather than one simple destination. The fascination lies in scale. Our entire region of space may be drifting within a gravitational story too large to picture from inside it. Huge cosmic voids raise questions about structure on impossible scales. The universe contains vast regions where galaxies are rare. These voids can stretch across enormous distances, separated by walls and filaments of brighter structure. In the standard view, they formed as gravity pulled matter toward denser regions, leaving emptier zones behind. Yet the scale of some voids can still feel surprising. They show that the universe is not evenly filled in any ordinary sense. It has a sponge-like pattern, with great hollows surrounded by matter-rich boundaries. Studying voids helps researchers test gravity, dark energy, and the growth of structure over time. Some people look at the emptiest regions and wonder whether something unusual carved them out. Others imagine they could be traces of cosmic events from before ordinary structure formed. The careful explanation remains powerful enough. Nothingness itself becomes a feature to study. A void is not merely absence. It is a giant clue about how the universe arranged its matter. The Bootes void looks emptier than simple models predicted. One of the most famous cosmic voids lies in the direction of the constellation Bootes. When it was first recognized, its size and emptiness startled astronomers. A region that large should contain far more galaxies if matter were distributed in a simple way. Later surveys found some galaxies inside it, so it is not truly empty. But it remains an impressive example of how uneven the cosmos can be on large scales. The Bootes void invites several interpretations. It may have formed through the merging of smaller voids. It may represent a natural result of cosmic structure growing over billions of years. Or it may point toward details in early conditions that we do not yet fully understand. Some people see such giant emptiness as more than a statistical feature. It feels like a missing chapter in the cosmic map. The strange thing is, not that space contains galaxies. It is how much room it leaves between them. Quasars shine with power that outmatches entire galaxies. A quasar can appear like a bright point of light, but its energy comes from one of the most extreme engines in the universe. At its center is a supermassive black hole surrounded by infilling material. As gas spirals inward, it heats to enormous temperatures and releases radiation across vast distances. Some quasars shine so intensely that they can be seen from the early universe, outglowing the galaxies that contain them. This makes them both beacons and puzzles. How did their central black holes grow so large so quickly? What turns one galactic center into a blazing quasar while another stays calm? Quasars also help illuminate material between galaxies, giving astronomers a way to study otherwise invisible gas. Some people imagine them as cosmic lighthouses from a more violent era. The factual mystery is just as impressive. A dark object, by feeding, can create one of the brightest sights in existence. Blazars aim cosmic beams straight toward Earth. A blazar is a special kind of active galaxy with a jet pointed almost directly at us. The jet comes from the region around a supermassive black hole where magnetic fields and infilling matter create a powerful outflow of particles and radiation. Because the beam is aligned with our view, the object can appear wildly bright and variable. Its light may change quickly, revealing violent processes happening near the central engine. Blazars are important because they let us study extreme physics under conditions impossible to create on Earth. They may also contribute to high-energy cosmic particles and neutrinos detected by observatories. Some people find them unsettling because the universe is not merely shining in all directions. In this case, a galactic engine is aiming a beam across space, and our planet happens to be in the line of sight. It is not a weapon in the usual sense. It is stranger than that. Pulsars keep time with an accuracy that feels unnatural. When certain massive stars collapse, they leave behind rapidly rotating neutron stars with beams of radiation sweeping through space. If one of those beams crosses Earth, we see a pulse each time the star turns. Some pulsars rotate with astonishing regularity, rivaling the precision of the best clocks. This made their discovery so surprising that artificial signals were briefly considered before the natural explanation became clear. The truth remains extraordinary. A dead star, only city-sized, can spin many times each second while sending a beam across the galaxy. Pulsars help test gravity, detect planets around other stars, and may even contribute to future navigation through deep space. Some are arranged in timing networks that could reveal gravitational waves from enormous cosmic events. The fascination is easy to understand. These are not ordinary stars twinkling softly. They are collapsed stellar cores acting like cosmic metronomes, keeping time with a steadiness that feels almost designed. Magnetars can release more energy than our minds can hold. A magnetar is a neutron star with a magnetic field so extreme that ordinary comparisons fall apart. It can disturb matter at distances where normal stars would seem harmless. Sometimes these objects unleash enormous flares that travel across the galaxy and affect detectors near Earth. The source is thought to be stress in the star's crust and magnetic field, but the exact behavior remains difficult to predict. A body only about the size of a city can carry a magnetic field strong enough to reshape atoms near its surface. That alone feels almost unreal. Some people imagine magnetars as cosmic warning signs, showing what nature can build when gravity and magnetism are pushed beyond familiar limits. They are not common, and most are hidden until they erupt. When they do, the message is clear. The universe does not need large size to create overwhelming power. Sometimes the most intense engines are compact, dark, and nearly invisible until they awaken. Gamma-ray bursts may be the universe's brightest sudden events. For a few seconds, a gamma-ray burst can outshine almost everything else in the observable cosmos. These flashes come from catastrophic events, such as the collapse of massive stars or the merger of compact stellar remnants. From Earth, they appear as sudden bursts of high-energy radiation arriving from deep space. The first detections were so unexpected that they raised serious questions about their origin. Now we know they are cosmic, but that has not made them feel ordinary. Their beams can cross billions of light-years and still be detected by instruments around our planet. Some bursts are followed by fading afterglows, which allow astronomers to locate their host galaxies. Others remain harder to understand. Some people wonder what such an event would do if it occurred too close to a living world. The thought is sobering, but also awe-inspiring. The universe can release, in a moment, more light than a galaxy makes in ages. Some explosions seem too powerful for known stellar deaths. Stars can die in many dramatic ways, but a few cosmic explosions appear to push against the limits of familiar models. Some are unusually bright. Some last longer than expected. Some produce strange chemical traces or unusual light curves that do not fit neatly into standard categories. These events force astronomers to ask whether the star was exceptionally massive, whether it interacted with nearby material, or whether an exotic engine was hidden at the center. Possible explanations include rapidly spinning neutron stars, unstable giant stars, or unusual black hole formation. The mystery is exciting because each strange explosion becomes a crime scene in deep time. The star is gone, but the light carries evidence of what happened. Some people see these events as hints that the universe has more ways to destroy and remake matter than our textbooks have listed. Every extreme blast expands the catalogue of what a dying star can become. Supernovae create elements that later become planets and people. The atoms in a rocky world do not appear from nowhere. Many were forged inside stars and scattered during violent stellar deaths. When a massive star explodes, it throws newly made elements into space, enriching gas clouds that later form new stars and planets. Iron, calcium, oxygen, and other familiar ingredients are part of this long cosmic recycling. Some elements form during the life of a star, while others are created during the explosion or in related extreme events. This means every solid thing around us carries a history older than Earth. A mountain, a seashell, and a human body all depend on earlier generations of stars that lived and died before the sun existed. Some people take this as a sign of deep connection between life and the cosmos. The scientific point is already astonishing. The universe had to become chemically richer before worlds like ours could form. We are late arrivals made from ancient fire. The first atoms formed before the first light could travel. In the earliest period, the universe was too hot and dense for ordinary atoms to exist. Particles moved through a bright, charged plasma where light could not travel freely for long. As expansion continued, everything cooled. Protons and electrons eventually combined to form the first simple atoms, mostly hydrogen and helium. That change allowed light to move through space without constant scattering. The universe became transparent, and the ancient glow from that transition still surrounds us today. This moment is crucial because it marks the shift from a foggy young cosmos to one that could later form structure. Before stars, before planets, before galaxies became familiar, the first atoms were quietly setting the stage. Some people imagine this as the universe gaining clarity for the first time. It was not a human kind of seeing, of course. It was the moment light began crossing space freely, carrying the oldest visible record we can detect. Hydrogen clouds may preserve memories of the early cosmos. Hydrogen is the simplest and most common element in the universe, but it is not boring. Vast clouds of it fill space between galaxies and within them. Some of these clouds carry clues from eras before many stars had formed. By studying how hydrogen absorbs or emits radiation, astronomers can trace the growth of structure, the heating of intergalactic gas, and the long transformation from darkness to starlight. In a sense, hydrogen is the universe's first archive. It records conditions that more complex objects may later erase. Some clouds remain almost chemically primitive, which makes them especially valuable. They may show how matter behaved before generations of stars filled space with heavier elements. Some people see this as cosmic memory written in the most basic material. A cloud with no obvious shape or drama may contain evidence from near the beginning of everything. The quietest gas can sometimes tell the oldest story. The first galaxies may have grown faster than expected. The earliest galaxies were supposed to be small, messy beginnings that slowly merged into larger systems. Yet observations have revealed young cosmic structures that appear surprisingly bright or developed. This has pushed researchers to reconsider how quickly gas can cool, collapse, and form stars in the early universe. Perhaps the first regions of matter were denser than expected. Perhaps star formation was more efficient under ancient conditions. Perhaps black holes and bursts of new stars made these galaxies shine brighter than their true mass suggests. The details remain under discussion, which makes the mystery alive rather than settled. For anyone who enjoys the unexpected, this is a thrilling development. The young universe may not have taken its time in the way earlier stories implied. It may have built complexity rapidly, almost urgently, turning simple gas into the first cities of stars, while cosmic history was still in its opening chapter. Giant black holes appeared surprisingly early in cosmic history. Some of the most distant quasars are powered by black holes with masses of millions or billions of suns. Because their light comes from a young universe, the puzzle is how they became so enormous so quickly. A black hole can grow by feeding on gas and merging with others, but there are limits to how fast this can happen under normal assumptions. This has led to several possibilities. The first seeds may have been larger than expected. They may have formed from direct collapse of huge gas clouds. They may have fed at unusual rates in dense, early environments. Some people wonder whether black holes were present almost from the start, shaping galaxies rather than simply growing inside them later. The mystery changes the usual picture. Instead of galaxies slowly building central giants, the early universe may have produced massive dark engines before anyone thought there was enough time. Some black holes may have formed before the first stars. Most black holes are thought to come from collapsed stars, but another possibility reaches further back. In the very early universe, tiny regions of extreme density may have collapsed directly into black holes before any star had time to shine. These are called primordial black holes. Their sizes could vary widely, depending on the conditions that created them. If they exist, they would be relics from the first fractions of cosmic history, carrying information from an era otherwise hidden from direct observation. Some researchers have explored whether they could make up part of dark matter, seed early supermassive black holes, or explain certain gravitational wave events. None of this is proven, but it remains a serious and fascinating possibility. Some people love the idea because it suggests darkness may have come before light. The first compact objects in existence may not have been stars at all, but silent gravitational knots from the young cosmos. Primordial black holes could be hiding as dark matter. Dark matter reveals itself through gravity, but it does not shine or interact with light in the usual way. Primordial black holes could fit part of that description if enough of them formed in the early universe. They would not need exotic particles, only regions that collapsed under extreme density. Different masses are constrained by different observations, so they cannot simply explain everything without difficulty. Still, some windows remain open, and the idea keeps returning whenever new data appears. If even a fraction of dark matter were made of these ancient objects, the implications would be enormous. The invisible scaffolding around galaxies might be partly composed of black holes older than stars. Some people imagine them drifting through the cosmos like hidden seeds from creation. The careful mystery is gripping enough. Instead of being made entirely of unknown particles, some of the universe's missing mass may be locked in ancient darkness. Hawking radiation suggests black holes may slowly evaporate. Black holes were once imagined as final prisons, taking in matter and giving nothing back. Quantum theory changed that picture. Near the boundary, subtle effects imply that black holes can emit a faint form of radiation. For large black holes, this process is incredibly weak and slow. Over enormous timescales, however, it suggests they may lose mass and eventually disappear. This idea is profound because it gives black holes a life cycle. They are not eternal holes in reality. They may age, shrink, and fade. The concept also connects gravity, thermodynamics, and quantum physics in a way that feels like a clue to a deeper theory. Some people wonder what happens at the final instant of evaporation. Does information escape? Does something remain? Could tiny, ancient black holes be ending today in detectable flashes? The answers are uncertain, but the possibility alone changes the feeling of cosmic darkness. Even black holes may not last forever. The information paradox still troubles the deepest laws of physics. When matter falls into a black hole, the outside universe loses access to its details. Yet quantum theory says information about physical states should not be destroyed. Hawking radiation made the conflict sharper because a black hole can slowly disappear. If it evaporates completely, what happens to the information that fell inside? This question has driven decades of debate and has influenced ideas about holography, quantum gravity, and the nature of space-time. Some proposals say the information is encoded at the boundary. Others argue it escapes in subtle patterns within the radiation. More radical views suggest space-time itself must be rethought. The problem sounds remote, but it is one of the clearest places where our best theories disagree. Some people see it as a crack in the official picture of reality. The mystery endures because it asks whether the universe keeps perfect records, or whether something fundamental can truly be lost. Singularities may reveal where our understanding breaks down. A singularity is not simply a very dense object. It is a sign that the equations have reached a point where they stop giving sensible physical answers. In black holes and early universe models, singularities appear when space-time curvature becomes extreme. Many scientists suspect they are not real objects in the usual sense. They may be warnings that a deeper theory is needed. Quantum gravity may replace them with something finite, a bounce, a transition, or an entirely new state of space-time. The mystery is powerful because singularities sit at the edges of our most successful theories. General relativity leads us there, then seems unable to continue. Some people imagine them as gateways, cosmic seeds, or places where reality changes phase. Those ideas are speculative, but the underlying problem is undeniable. A singularity marks the boundary between what our mathematics can describe and whatever nature is actually doing beyond the limit. The center of a black hole may not be a point. The old image of black holes suggests all infalling matter is crushed into a single point of infinite density. Many researchers doubt that this literal picture is correct. Infinite values usually indicate that a theory has been pushed beyond its proper range. At the center, quantum effects may become essential, and they could prevent a true point from forming. Some models imagine a dense core, a bounce into another region, a fuzzball of quantum states, or a structure unlike anything in ordinary experience. None has been confirmed because the interior cannot be directly observed from outside. Still, the question matters because it may reveal the true relationship between gravity and quantum mechanics. Some people are drawn to the idea that black holes are not dead ends, but hidden transformations. The center may not be a place where reality vanishes. It may be where reality becomes something we have not yet learned to name. Our galaxy may contain many unseen stellar graveyards. The Milky Way shines with hundreds of billions of stars, but it also contains the remains of stars that no longer glow in ordinary ways. White dwarfs cool slowly. Neutron stars can fade from easy detection. Black holes may drift through space without feeding, making them almost invisible. Over the galaxy's long life, many generations of stars have been born and died, leaving compact remnants scattered through the disk and halo. Some may pass near ordinary stars and reveal themselves through gravitational effects. Others may remain unknown for immense stretches of time. This means the galaxy is not only a living city of starlight, it is also a cemetery filled with dark objects and quiet remains. Some people wonder how many unseen black holes move near us without notice. The idea is not meant to frighten. It deepens the map. The Milky Way has a hidden population made from the endings of stars. Sagittarius. It changes quietly at the Milky Way's heart. At the center of our galaxy sits a supermassive black hole with a mass of millions of suns. It is not as wildly active as some galactic centers, but it is not entirely still. Gas, dust, magnetic fields, and nearby stars move through its environment. Occasionally it flares, suggesting material has heated or shifted near the edge of capture. By watching stars orbit close to it, astronomers have measured its mass and confirmed its presence with remarkable precision. More recent images have revealed the glowing material around its shadow. Yet many questions remain. Why is it so calm compared with other central black holes? Did it erupt more strongly in the past? Could old bubbles and energetic traces around the galaxy be signs of earlier activity? Some people imagine the Milky Way's center as a sleeping engine. It is not dead. It is waiting, changing, and feeding only in small moments. The Milky Way may have swallowed many smaller galaxies. Our galaxy did not form as a finished spiral in isolation. Evidence suggests it grew by merging with and absorbing smaller galaxies over billions of years. Streams of stars around the Milky Way act like remnants of these ancient encounters. Some star groups move differently from the main disk, preserving the motions of systems that were pulled apart by gravity. This means the galaxy above us is partly built from cosmic archaeology. Its halo contains debris from vanished neighbors. Its structure carries traces of collisions that happened long before human history. Some people see this as a reminder that galaxies are not peaceful islands. They are evolving systems that feed, merge, and transform. The stars we call familiar may include immigrants from lost galaxies whose names we will never know. The Milky Way is not a single story. It is a collection of older stories pulled into one vast rotating home. Andromeda is already moving toward a future collision. The nearest large spiral galaxy is not drifting away with the general expansion of space. It is moving toward the Milky Way. In several billion years, the two galaxies are expected to interact and eventually merge into a larger system. The word collision can be misleading. Because individual stars are so far apart, the direct impacts will be rare. The real drama will be gravitational. Star orbits will change. Gas may be stirred into new star formation. The shapes of both galaxies will be transformed over enormous timescales. For now, Andromeda appears as a faint smudge to the naked eye under dark skies. But it is also a future partner in a cosmic merger. Some people find it strange that the night sky already contains our galaxy's destiny. We are looking at an approaching structure so large that its arrival will rewrite the architecture of everything around us. Dwarf galaxies may reveal secrets larger galaxies have erased. Small galaxies are easy to overlook, but they may preserve clues that bigger systems have lost. Because they contain fewer stars and often evolve more slowly, some dwarf galaxies retain chemical and structural evidence from early cosmic history. They can show how the first generations of stars enriched their surroundings, how dark matter behaves in small systems, and how galaxies form when gravity has less material to work with. Some are companions of the Milky Way. Others drift more independently. Many are faint, making them difficult to detect until careful surveys reveal them. The mystery is that their motions sometimes raise questions about dark matter and galaxy formation. Some people wonder whether satellite galaxies are arranged in patterns that standard models struggle to explain. Whether those patterns are meaningful or temporary, dwarf galaxies matter. They are not lesser chapters. They may be the footnotes that expose what the grand story has missed. Starless galaxies may exist almost entirely as invisible matter. A galaxy is usually imagined as a gathering of stars, but some objects may be dominated by gas and dark matter with very little starlight. These faint systems are difficult to find because they do not announce themselves with bright stellar populations. Astronomers look for hydrogen signals, gravitational effects, or unusual motion that hints at unseen mass. If starless or nearly starless galaxies exist in significant numbers, they could change how we count cosmic structure. They would show that dark matter halos can form without easily turning gas into stars. That raises questions about what conditions ignite star formation and what conditions prevent it. Some people imagine these objects as ghost galaxies, present through gravity but almost absent to the eye. The idea is fascinating because it challenges the meaning of a galaxy itself. Perhaps some cosmic cities were built with invisible foundations, but their lights never came on. Some stars appear older than the universe should allow. A few ancient stars have produced age estimates that seem uncomfortably close to, or even slightly older than, the accepted age of the universe. In most cases, the likely explanation is measurement uncertainty. Estimating stellar ages is extremely difficult because it depends on brightness, composition, distance, and models of how stars evolve. Still, these cases are exciting because they test the consistency of cosmic history. A star cannot truly be older than the universe that contains it, so any apparent mismatch points to something important. Either the star's age has been overestimated, the cosmic age needs refinement, or some detail in stellar physics has been misunderstood. Some people see these stars as rebels against the official timeline. The careful view is that they are precision tests at the edge of what we can measure. Either way, they are valuable. An old star can make the universe prove its own calendar. Tabby's star dimmed in patterns that invited unusual theories. This ordinary-looking star became famous when observations showed irregular dips in brightness that were difficult to explain at first. The dips were not the neat pattern expected from a planet passing in front of a star. They varied in depth and timing, which made the case feel strange. Natural explanations include dust, fragments of comets, or material orbiting in uneven clouds. Over time, dust became a strong candidate because different colors of light dimmed differently. Yet the early mystery opened a door that many people found irresistible. Some wondered whether a huge artificial structure could be blocking the starlight. That idea was speculative, but it turned the star into a public symbol of cosmic possibility. The most likely answer may be natural, but the fascination remains. A single star flickered in a way that made people ask whether advanced engineering could ever be noticed across interstellar distance. Boyajian's star still reminds us how strange starlight can be. The same famous object carries another lesson beyond its unusual dimming. Starlight is not just brightness. It is a stream of information, and tiny changes can raise enormous questions. When a star varies in unexpected ways, astronomers must consider dust, magnetic activity, orbiting debris, instrumental effects, and unknown astrophysical behavior. The process shows how quickly a distant point of light can become a mystery with competing interpretations. It also shows why caution matters. A strange signal does not automatically mean an alien cause, but it also should not be dismissed before the evidence is understood. Some people love this case because it briefly made a serious scientific search feel like a late-night conversation about impossible civilizations. That is part of its legacy. Even when the explanation leans natural, the door it opened remains important. The universe can still surprise us through something as simple as a star becoming slightly dimmer than expected. Dyson spheres remain a serious thought experiment about advanced civilizations. An advanced civilization with enormous energy needs might try to capture a large portion of its star's output. The imagined structure is often called a Dyson sphere, although many realistic versions would be swarms of orbiting collectors rather than a solid shell. The idea began as a thought experiment about how a technological species might become detectable from far away. If such engineering existed, it could produce unusual infrared signatures as starlight was absorbed and re-radiated as heat. Searches have looked for possible signs, but no confirmed example has been found. Still, the concept remains fascinating because it gives alien life a practical shape. Instead of waiting for messages, we might search for evidence of large-scale energy use. Some people see Dyson structures as one of the clearest bridges between imagination and observation. The question is simple and enormous. If intelligence grows long enough, could it reshape an entire solar system? Alien life may be common, yet still nearly impossible to find. The ingredients for life appear widespread. Many stars have planets. Some worlds orbit in regions where liquid water could exist. Organic chemistry also appears in space. Those facts make life feel plausible beyond Earth. Yet detection remains incredibly difficult. A planet may host simple organisms without producing obvious signals across interstellar distance. A living ocean under ice may leave only subtle chemical hints. A civilization may be brief, quiet, or using technologies we do not recognize. Distance makes the problem harder because even nearby stars are remote by human standards. This creates a strange tension. Life may be scattered throughout the galaxy, while proof remains rare or absent. Some people believe the universe is crowded, but hidden. Others think life itself may be the rare miracle. The mystery is powerful because both possibilities feel extreme. Either we are nearly alone, or we are surrounded by life that has not yet found a way to speak clearly. The Fermi paradox makes silence feel like evidence. If the galaxy is old, vast and full of planets, then one might expect signs of other civilizations. Yet we do not see obvious visitors, clear signals, or unmistakable engineering across the sky. That tension is known as the Fermi paradox. The silence can be interpreted in many ways. Perhaps intelligent life is rare. Perhaps civilizations do not last long. Perhaps interstellar travel is harder than hopeful theories suggest. Perhaps advanced beings deliberately avoid contact or use methods beyond our detection. Some people wonder whether the quiet is not empty at all, but carefully maintained. Others think we are listening at the wrong frequency, at the wrong time, with the wrong assumptions. The paradox is so haunting because it turns absence into a question. The night sky gives us no simple answer. Its silence may mean we are alone, unnoticed, protected, ignored, or simply too young to understand what we are hearing. Civilizations may vanish before they can cross the stars. A technological society has to survive many dangers before it can become truly interstellar. It must manage energy, environment, conflict, disease, artificial intelligence, and unknown pressures that come with rapid advancement. Even without dramatic catastrophe, a civilization may lose interest, turn inward, or remain limited by economics and physics. This possibility is sometimes called a great filter. Somewhere between simple life and star-crossing intelligence, there may be a barrier most worlds do not pass. Earth may be before it, inside it, or beyond it. No one knows. The idea is unsettling because it connects cosmic silence with the future of our own species. Some people wonder whether ancient alien civilizations rose and disappeared long before humans looked up with instruments. Their ruins might be too far away, too faint, or already erased by time. The mystery is not only out there. It asks what it takes for intelligence to endure. Panspermia suggests life may travel between worlds. Life may not always begin separately on each planet. One possibility is that microbes, or the chemical precursors of life, can move between worlds inside rocks blasted away by impacts. We know that material can travel from Mars to Earth because meteorites from Mars have been found here. Whether living organisms could survive the journey, the cold, the radiation, and the violent arrival is still debated. Some hardy microbes on Earth can endure astonishing conditions, which keeps the possibility alive. A broader version imagines comets and dust carrying organic ingredients through space. An even more speculative version suggests deliberate seeding by an advanced civilization. The idea matters because it changes the meaning of origin. If life can spread, then two living planets might share ancestry. Some people find that thrilling. Earth life may not be a sealed local story. It may be one branch of a much older cosmic exchange. The simulation idea turns the whole universe into a mystery. The simulation hypothesis asks whether reality could be generated by an intelligence or system beyond our own level of existence. The thought often begins with future technology. If advanced civilizations could create convincing simulated worlds with conscious beings inside them, then perhaps simulated realities would outnumber original ones. That does not prove we live in one. It only makes the possibility difficult for some people to ignore. The idea attracts attention because physics already describes reality through information, rules, limits, and measurable states. Some see that as suggestive. Others argue it is just a modern metaphor projected onto the cosmos. The challenge is testing it. What evidence would count? A glitch, a boundary, a hidden pattern, or a limit in physical law could all be imagined, but none is confirmed. The mystery is unsettling because it turns every ordinary experience into a clue. The universe may be real in a way we understand, or real in a way we do not. Consciousness may be the universe trying to understand itself. Matter became stars. Stars made heavy elements, and those elements eventually became brains capable of asking where everything came from. That fact alone is astonishing. Consciousness remains one of the deepest mysteries because subjective experience does not easily reduce to physical description. Neurons can be studied, signals can be measured, and behavior can be observed. Yet the inner feeling of awareness remains difficult to explain. Some believe consciousness emerges from complex information processing. Others suspect it is more fundamental, perhaps connected to the structure of reality itself. More speculative voices imagine mind as a feature woven into the universe, not merely an accident within it. No view has ended the debate. The final mystery may not be far away in a galaxy. It may be the fact that the cosmos produced beings who can wonder about galaxies at all. Through consciousness, the universe has become aware that it exists. And so we come to the end of our journey through the mysteries of the universe. Tonight, we have moved from the largest questions of all to the smallest hidden structures beneath reality. We have followed the pull of dark matter through spinning galaxies. We have watched space stretch under the influence of a force no one fully understands. We have stood at the edge of black holes, where information, time, and gravity begin to lose their familiar shapes. We have passed through frozen moons with hidden oceans, wandering planets without suns, and ancient signals crossing the dark between stars. We have looked towards strange patterns in the first light of the cosmos and wondered whether our universe is alone or only one part of something far larger. We have imagined civilizations that may have risen elsewhere, messages that may never reach us, and forms of life that could be waiting in places no human eye has seen. And still, after all of that, the mystery remains. Perhaps that is what makes the universe so powerful. It does not give itself away all at once. It lets us find a clue, then another, then another. And just when we think we understand the shape of the story, the darkness opens a little wider. If you enjoyed this journey, you are warmly invited to like, subscribe, or leave a thought below. It helps others find their way here too. And if you happen to still be awake, there will be another mystery waiting for you on the screen. But for now, there is nothing more you need to solve. Let the questions drift away. Let the stars become distant again. Let your breathing slow and allow your body to settle into the quiet weight of rest. The universe will keep its secrets for another night. Sleep well and good night.